This next ODE is going to have some interesting behavior for the existence and uniqueness theorem. So let's go ahead and dive in here. And so apply the existence uniqueness theorem. The first thing that we need to do is we need to get this differential equation into this format: y prime equals some function f of x comma y. Okay, well that isn't too terrible. So if we subtract the y over to the right hand side and then we divide everything by x, we'll get y prime by itself. So that'll be y prime equals, so 3x squared divided by x will just give me 3x, then minus y divided by x. All right, so that's f of x comma y. So let's take a look. We have, that's f of x comma y. What about, f of x comma y? What about partial f partial y? Right, well that's partial derivative with respect to y of this 3x minus y over x. Okay, so right, treat the x's as constants, so the partial derivative with respect to y of 3x is just 0. And the minus y over x, that y is going to turn into 1, and that 1 over x is treated like a constant, so we just get a minus 1 over x. So it's just minus negative 1 over x. All right, so where are these discontinuous? So we have a problem here. When x is 0, we're going to get division by 0. So that's a problem. And in partial f partial y, we have the exact same problem. It's a little different equation, right? But it's still a problem. 1 over 0 is going to be a problem. So we have f of x comma y and partial f partial y are discontinuous at x is equal to 0, meaning on the y-axis. So as long as the initial condition isn't on the y-axis, we should be fine. There should exist a unique solution, and we're good. So that's all the existence and uniqueness theorem can tell us, but there actually turns out to be some interesting behavior on the y-axis. So let's go ahead and figure that out. And the only way to really figure it out is to solve the original, the ordinary differential equation. So looking back here, we have x, y prime plus y equals 3x squared. We can solve this using integrating factor. And actually one thing nice about this ODE is it's already kind of in the nice format for integrating factor. So right, if I go down here and I have x, y prime plus y equals 3x squared, this actually already collapses backwards in a reverse product rule into xy, the whole thing prime. Right, because x, this is the half of the product rule where I took the derivative on the second term, and this is the half of the product rule 1 times y where I took the derivative on the first term. Right, x turns into 1. So we're actually good there. And then I'll leave a little room here. On the other side, it's still 3x squared. Now we can integrate both sides with respect to x. All right, so the integral and derivative essentially cancel, so we end up with xy equals 3x squared turns into x cubed, and we get our constant of integration. Then if we want to solve for y, we can just divide everything by x, so we get y is equal to x squared plus a constant over x. All right, well I can see maybe why the existence and uniqueness theorems had some trouble, because it looks like, we have division by x. But let's go ahead and take a look and see what all the solutions to this thing look like for different values of c. So right, we have this y. Oops. We have y equal to x squared plus c over x. So the first bit here, we have the x squared. All right, so x, and I'll just leave that alone there. It's the parabola, so there's only one of them, there's no consonant, so something like that. But then we also have a couple more. So there's a few options here. We've got x, and we've got c is less than 0. And here I'll put, y equals x squared there. Here y equals c over x. All right, if c is less than 0, then it has a vertical asymptote along the y-axis, but it's going to look something like this. See, okay, that came out reasonably well. Right, so that's the c less than 0 case, and then the c greater than 0 case. It's pretty similar. It's reversed though. So c greater than 0, we have y equals c over x. That'll look something like this. All right, so now what if we start, adding these together to get different solutions? So now I'm going to do a big graph. We've got x, we've got y. I think I'll put that y up a little higher. I'll need the room. All right, so let's start out. Let's say c is greater than 0. Let's start with those. If c is greater than 0, then I'm adding kind of this graph to this x squared graph. All right, so in the x squared graph, when x is near 0, x squared is approximately 0. It's close to 0. It's a small number. But the opposite is true in this graph. When x is close to 0, we actually get a really huge number, and we either get a huge positive number or a huge negative number. And so when x is slightly positive but close to 0, and c is positive, we get a graph that looks something like that. It looks a lot like this curve because x squared is fairly small around there. But then as x gets larger and larger, positive, then this thing becomes close to 0, and this thing gets really, really big. So it starts to look more and more like the parabola. So something like that. But then on the other side, if x is slightly negative, x squared is small, but this is a super duper negative number. So it's going to look something like that for a while. But then x squared takes over, it becomes really big and positive, and this thing gets slightly negative and close to 0. So it'll actually do something like that. And then it makes more and more of them. So over here, if c is a slightly different positive number, we'd get another that looks like that, another that looks like that, another that looks like that. And these are all the c greater than zeros. And over here, I'm not going to be able to draw them very well. It's hard to do, but kind of just moves them out further and further. And these are the c greater than 0. All right, well, that was c greater than 0. What about c less than 0? Well, it's kind of the flip of the other one. So, right, if I have c is less than 0 and I'm slightly positive, so x squared is fairly small, but this is a huge negative number. So it's going to look a lot like the vertical asymptote. All right, but then as x gets larger, this thing gets smaller and smaller, but slightly negative, and this one gets really, really positive. So it'll do something like that. And then there'll be a whole set of them as you keep changing c. I didn't draw that one that well, but here we go. So then these are c less than 0. Then similarly, on the left, when x is slightly negative, this is a small positive number, but this is a huge positive number, so it's going to look like that. But then as x gets more and more negative, x squared gets really big, c over x gets really small, so it'll do something like that. And then there's a whole set of them. All right, so then this one is c less than 0. And so you can actually make c smaller and smaller and smaller, and they'll hug closer and closer to the y-axis. But it'll actually never touch it, right? All of these things asymptote towards x equals 0, the y-axis. But it doesn't really touch it. But there's one case that kind of breaks the rule. What if c is 0? If c is 0, we're not adding this one, we're not adding this one, we're just adding x squared. So if c is 0, we get this thing that's actually dividing all the different regions. So if I try and draw that, and I manage to go through the origin, up, this thing right here is c equal to 0. And so it looks like we might have a function that actually solves the differential equation, that the function is unique and you can actually have an initial condition on the y-axis, but only one point on the y-axis. All these other points don't have solutions. So let's just double check that. So we've got this possible solution. Y is equal to x squared. Okay, well, if y equals x squared, we had our function xy prime plus y, and we want to know, does that really equal 3x squared? All right, so we have x, y prime is going to be times 2x, then y is x squared. And we're wondering, does that really equal, that's a terrible question mark, does that really equal 3x squared? And the answer is yeah, it does. So in here, 2x times 2x is 2x squared, and you've got another plus x squared, then yeah, that's definitely 3x squared. So this actually is solving the original differential equation, but if we go back, we had this y prime when we solved just for y prime, it equals, where was that? 3x minus y over x. There's a removable discontinuity if y equals x squared. So we could have, x squared prime equals 3x minus x squared over x. There is a discontinuity here, but it's a removable discontinuity. That's kind of where the existence and uniqueness theorem had a problem. But it is removable, so yeah, this looks like it's a function that will solve the differential equation, this y equals x squared when c equals 0. And so this just goes to show you, there can be some really weird things that happen with fairly simple looking differential equations. And the existence and uniqueness theorem can guarantee us solution, there's at least one solution, and existence can guarantee there's exactly one solution whenever we meet the conditions, in particular that f and partial y are continuous in a region around the point. But if those conditions aren't satisfied, we might end up with no solutions, which happened on most of the y-axis, but on one part of the y-axis, we actually ended up with exactly one solution. Right, so again, this, A implies B, statement A implies statement B. If we don't meet the conditions of f and partial y continuous, anything could happen with the number of solutions. They could not exist, there could be one, there could be more than one. And we'll see that in the next examples as well.